Thank you, and thank you very much to the organizer for inviting me and giving me this opportunity to present these results. This conference has been great so far, so hopefully I can contribute a little. So my setting is the following. Imagine you have some proper geodesic metric space. You have a countable group which acts on gamma by isometry. On X, thank you. And I assume that the action is proper. And in all my results, I will have very nice situations. Which is just the following. You imagine that you have some manifold. As you see, it's not compact. But the curvature is negative. And X is just the universal cover with the lifted metric. And gamma is the fundamental group of my manifold. So this is the very nice setting. Then I have the nice setting where my space is a cat minus one metric space. I have a convenient setting where my space is Gromov hyperbolic. And I suspect that the good setting for most things I will tell you is just to assume, so my action is proper by isometry, is just to assume that gamma has a contracting element. And no more assumption than proper geodesic space on X. So the results which I will tell you, most of them has been proved there or in the cat minus one setting. As I will explain, I know how to extend, or it's already written, to Gromov hyperbolic setting. And we're currently working, especially with Remy, on the extension of these results in the general setting with the contracting elements. So what kind of question will I ask? It's what I call asymptotic counting problem. So you fix some point in your metric space, some positive number, and you look at what I will write the counting function for gamma acting on X with base point X, which is just the number of element in gamma such that the displacement from X to gamma X is at most R. And the question is, the general question is having asymptotic estimate, if possible equivalent, when R goes to infinity. Not necessarily. If you imagine that I'm the fundamental group of such a manifold or a surface, you see I've allowed topology to infinity. And most of the questions which I will ask in the smooth setting, they are not interesting when my group is co-compact. In the hyperbolic setting, they're already interesting when it's co-compact. But you have to imagine that when you want to go from co-compact smooth to non-compact smooth, the kind of problem you find is very similar to the kind of problem you enter when you want to go from smooth to non-smooth. And let me give you two theorems. The first one, well, has a long history, whose one of the main names is Margulis. And the form which I will write is due to Roblin in O3, saying that if XD is a cat-1 space, then you only have two possibilities. First, for all x in X, there is constant X, such that your counting function is equivalent to these constants times a purely exponential. I will say more about this delta gamma, but we already have met it several times. It's the exponential growth rate of the group. Or it's negligible before this exponential growth rate. And I want to tell you what are natural geometric criterion to be in one or another situation. Okay? I really mean that the quotient is 1. It's not bounded by multiplicative constants. So in part, it's stronger than having purely exponential growth. Yep. Right. Yep. So maybe I should have done some picture. I have my space XD. I have some element X with its orbit. Some colors. I have a ball of radius R. And the entropy, or critical exponent, definition, the entropy of the critical exponent is, you look at your counting function. It grows usually exponentially fast, so you take a logarithm, divide by R, and take a limit. So it's, if you want to prevent question, you can put a lim sub. Actually, it's a limit, but it's not trivial. Yep. No, good point. It's independent of X. Because basically, if you change X by some triangle inequality, you will have some factor which will be killed by the log and the radius. Let me give two examples. Well, a family of examples. So, if x over gamma is a smooth compact manifold of negative curvature, then it's purely exponential. Then so when you have constant curvature, this is due to Selberg and Huber. And if you're on variable curvature, this is the thesis of Margulis. Now, if you imagine the following setting, so you have a covering from a compact negatively curved manifold. And my x over gamma is here. So if x over gamma is an abelian cover, a ZD cover, over, let's say, a compact manifold. Still with negative curvature. Then you have asymptotic counting function. This is due to Richard and Mark Policott. '94. Your asymptotic counting function is equivalent to some constants, depending on the base points, to exponential terms, divided by r to the power d over 2. So you're in the second setting, and you have a precise asymptotic. And which you can see that somehow here you have infinite geometry, and here you have finite geometry. Now I will give you, and it's important to realize that until less than 10 years ago, like probably 2015, there was no other example where we had precise asymptotic equivalent, which was not of the pure exponential form. So let me give another example. And let's call this an exotic surface example. So I will take a very basic surface. I have a surface with two infinite trumpets and one cusp. So, and this is x over gamma, and this is my x. And gamma, which is the pi 1 of my surface, let's call it sigma, is just the free group in two generators. And in this context, the action of this element is called parabolic, and this one is called hyperbolic. And now, first thing. So here, I can decide which Riemannian metric I put on, and depending on the Riemannian metric which I will put, I will be in one or another situation. Okay? So, first thing, if the curvature is always -1, okay, then my growth function, which depends on the distance, on the metric, is given by some constants and exponential. This is false even when the curvature varies between -1 and -1 minus epsilon. So let me detail the construction. Right. I will do the following. I have my cusp with some zero level. Some A level. And some 2A level. And inside the cusp, I will change the metric. Okay? So the metric in the cusp if I call t the vertical direction, so the cusp is just a circle times 0 plus infinity. And the metric is some constant, which depends on the size here, times dt square. Oh, dt is for here, so exponential minus 2t d theta square plus dt square. A hyperbolic cusp is just exponential decrease. Okay? This is when the curvature is -1. And now, for t less than a, I keep this metric. And for t bigger than 2a, I take as a new metric, let's call it GB, which is the same constant, but I add some polynomial factor for some b, which has to be bigger than 1. Okay? So all here, I have kept curvature -1, and above there, here I've put a new metric. And here is just a smoothing procedure in order to ensure that the curvature stays bounded. the theorem is the following. So it has many inputs. The original construction is a variation on construction by Dalbo, Hotal, Peignet. It's not exactly this one, but never mind. The most results which I will state are either from the thesis. So this is in 2000. Vidotto is in 2016. This one is in 2018. So if the original size of the cusp at the very bottom is large enough, which you can always assume playing with your attachment space, then there exists some critical value such that if the height where I change my metric is far, so my perturbation is far enough from the constant curvature setting, then the critical exponent is strictly bigger than 1/2. And the asymptotic counting function is of purely exponential type. If you have a strong perturbation up to some small a, if a is less than this critical value, then the critical exponent for the whole group is equal to 1/2. And actually, your counting function is equivalent to some constants over r to the power b, where the b is the one where I have perturbed my metric. And when you are exactly on the critical value, it depends on b. It's either the same as in this situation when b is bigger or equal to 2, or two minus b if b is between 1 and 2. So, yeah. Thank you. So for all those who know what this term means, it means that the action of gamma being geometrically finite is not a good criterion for asymptotic orbital counting. So when your space is the hyperbolic plane, geometrically finite really means that in your quotient, you just have a finite number of trumpets and cusps. And this generalizes for relatively hyperbolic groups. But I don't want to enter into this definition because this is the prototypic examples. And this result shows that it does not at all explain the dichotomy between purely exponential asymptotic counting and non-purely exponential. Yep. It's always bigger than 1/2. No, because of the trumpets. If you're in finite volume, then it's 1. But as soon as you have at least one trumpet, then it's strictly lower. Yeah. And as we will see, this strict inequality here and there are the key assumptions to ensure that, because it is the critical exponent, I will write that, of the parabolic. So actually, there is a general result. So assume that I'm in a very nice setting. So x over gamma it will be my P1, P2 is geometrically finite with parabolic subgroups P1 up to PR. We have a theorem. It's a combination of d'Albo au Talpeigné plus Roblin, which tells you that if the critical exponent of the whole group is strictly bigger than the maximum of the critical exponent of the parabolics, then we're in the purely exponential case. And now what I want to explain you is what this condition means in general for a group action, which may be much more complicated than being the pi1 of such a surface. In particular, what it means, even if your group is not relatively hyperbolic. Let's say that I had written somewhere one history, that now is 2 entropy at infinity. So I have my metric space. I fix some compact set. Okay. And I'm going to look at the orbit of this compact set. And I will define the first return to K subset of gamma. What is this? It's all the elements in my group such that there exists X and Y in my compact setting, such that when I look at the intersection between the geodesic or a geodesic, if it's not unique, this K, with all the orbit of K, and I don't want Y, I want gamma Y, I will make a picture immediately. Then this is included only is in K union gamma K. What does this mean? This one is in gamma K. This one is also. This one is also. But all these one are not in gamma K. Because I cannot go from K to K without crossing one of these images. If you think about the picture in the quotient, it really means that somewhere you have your compact. So this is X over gamma. This is K over gamma. This arc corresponds to some arc in gamma K. But if you go from here, you cross gamma again, and then go away and come back, this is not in it. Okay? And I will call entropy at infinity what it is the limit when r goes to infinity of the critical exponent for gamma k. Let k be just a big ball. So I'm taking k being bigger and bigger and bigger. So it's also, maybe it's easier to state like that, it's the infimum on all compact sets of the critical exponent of just my first return subset. Okay? Yes, it's not fully obvious. When you're in the cat -1 setting, you can show that when k increase, the critical exponent of gamma k decrease. It's not fully obvious because when k increase, you have more freedom to choose your arcs, but you also have more obstacle you have to rule out. And it can be shown that the obstacles are much more numerous than the freedom you get. And when you're Gromov hyperbolic, it's not fully true that it's increasing, but it's increasing up to, it's decreasing. But still, the infimum and the limit when it goes to infinity are the same. It is minus infinity. If some compact sets K has a gamma K containing all closed geodesics. Okay, let me put a t minus 1. So that's really when all closed geodesics are in there, starting from some t, you will have no more elements in gamma k. So the two results I wanted to state are the following. One is the combination of Fitz, Schapira, 1000, and Roblin. Say that at that time it was in a smooth setting. Actually, it doesn't really matter. Then the asymptotic counting function is purely exponential if and only if you have two conditions. The first condition is that the sum for all gamma of minus delta gamma distance the x at gamma x is infinite. And the second condition is that for some k, or all big enough, this is equivalent, the sum only on the first return arcs is finite. I will finish by stating one result and one conjecture. One result which I had shown is Barbara Schapira, which is 18. If the whole critical exponent of the group is strictly bigger than the exponent at infinity, then we have purely exponential groups. And the conjecture that if x over gamma is a smooth, negatively curved manifold, and we have this condition I call the critical gap, then there exists some positive number such that we have our purely exponential term plus some strictly exponential less remainder. And I'll stop here.